So this paper is published in 2019, and it's kind of based on the previously published paper. I know this because I know that site and I know the authors, and we talked about this, and I was interested to put this paper out for some time. Actually, I did visit this site as well, study site, several times. It's a fascinating place. And when you're there on the ground, you actually have a totally different feeling. So let's have a look on the paper itself. So here on the my picture, you can see I just took a picture of the area and these little hills where you see the fences going through. This what we will talk about, this deposit. Deposit, it's just the material that's been brought into the valley. This paper was published in Journal of Quaternary Science, and I'm quite sure this paper, if you want to read it, you have to pay something like $30 or something like that. So they will give you the abstract in modern journals. Majority of the modern scientific journals will give you abstracts, some pictures, maybe conclusions, but they're not going to give you like whole paper. And especially like usually people have supplementary material where they put some data, actual samples, information, this kind of stuff. So all of that, if you're at university or student, or you have access or have friend who at university, they can get this paper for you. Otherwise, you can ask authors, and they're usually very happy to email you the copy. But otherwise, you have to pay for it. So that's another kind of limitation of the science, I think, today. So people cannot actually read the papers and see what's going on. I got this paper from a friend, so I didn't have a problem. But also there's some journals, scientific journals, that start putting everything for free online, and I think that's the future, so quite happy about that. So let's have a look on the paper itself. It's quite a big paper. I read it only once, just before today, before my live stream. So just open it here. Here you can see it now. So there's 4 authors, and Samuel McCall's the main one, as I know, and he'd been working before on the site. In 2011, as I understand, he published the previous paper as part of his PhD about the site. So the idea is the Hillocks, it's this hilly site, and it's related to my video when I talk about Kyrgyzstan, if you watched my Hillock moraine video. And actually I need to finish that as well, and I will make it as a live stream as well, because it's quite complicated to do a separate video. So here, similar situation, we have these hills. That's why they're called hillocks. You can see here red dots. It's all these dot hills spread. It's not the sheep walking around New Zealand. There's a sheep too, but this is the hills, and you can see here on top of map. I think it's a later map scan, a little bit better. But when you're on the site, you can see there's a people for scale, and you can see these hills. So that's how it actually look like. It's not that quite straightforward in the field, but you definitely know there's some kind of hills, and nobody knows where they come from. So that's the site, and traditionally we have the idea that this is the glacial deposit. So back in the day, in this big valley, I will just show on this map, it was preoccupied. You see the Dart Glacier, it's the catchment of this river, which flows into the Lake Wakatipu, which is the famous New Zealand lake. And if you were ever been tourist South Island, you probably traveled to Queenstown. It's located here, and this place been in the movie of Lord of the Rings as well. So I have to mention this because I'm a big fan of Lord of the Rings. And when I watch these movies, I'm just, this is this site and this is these deposits. So that's how I watch Lord of the Rings. So anyway, there's a chunk of the videos filmed in this area. I think they kind of filmed it just here, just south of Queenstown. And remarkable, so it's the slopes, big hills, big mountains in the video, in the movie as well. So that's the lake, and it's past glacial lake. So there used to be ice back in the day when it was ice age on our planet, and the poor people in Europe, like Neanderthals and Cro-Magnons, were fighting for existence with the ice, which constantly froze everything. in New Zealand there was a glaciers too. You will not believe this, but it happened, and it's a very good site. New Zealand actually in general very good place to study glaciology, glaciers of the past, and compare it to Northern Hemisphere, because Northern Hemisphere we have so many sites, but in Southern Hemisphere there's more ocean and less land, so it's a little bit tricky to find any evidence. So that's the valley, and the ice was, now it's just there on top. You see those blue things? It's where the today's glaciers preserved. But in the past, the ice was here all over, through the lake till here, till the Kingstown, I think it's called, south. So the moraines, and we'll have a look on the Google Earth, preserved here, the terminal, the final kind of end point moraines of the ice that was sitting here in the last glacial maximum. I talk about this in my videos about last glacial maximum. You can have a look. So it was a big ice, and then in the last 20,000 years it's melted away slowly. And why it was melting away, you know, it's plugged out this how called trough, you know, like a deep depression in the mountain between two big slopes where the ice was sitting. And when it was retreating, there was a lot of water and rocks coming out of it and washing everything, melting everything, and it's left this lake because it also was a lot of water which ice melted, and it's not, you can see, not very easy access to the ocean to drain. So the deep trough accumulated a lot of water, and it's still supplied by all these little glaciers in the valley, not as much as during the retreat, but that's the reason of creation and existence of the lake here now. And we have this site here. It's kind of just getting up in a wider area of this valley, away from the modern shore of the lake. You guys can see my no, you cannot. Yeah, you can see my button. That's good. My mouse. So here there's the deposits, and traditionally, yeah, here Mount Alfred, and between Mount Alfred, traditionally this deposit was considered to be the way, the point where the glacier kind of stayed for some time and created this deposit. So people thinking this is definitely rocks and material that have been brought by ice back in the day, whatever 1,000 years before present, and then the glacier melted. And you can see the river going through here, so it's been washed a lot, and we don't have much preserved. Like everything in this valley, whatever was preserved during the glacier retreat, been washed away or destroyed by the very, very active rivers. In New Zealand, very active rivers. And they carry a lot of rocks. And they're quite active, especially in times of when there's a lot of rain. So they can flooded everything, demolished everything. And then on a good day, it's very lovely. So you will never even know about this. So rivers doing this thousands of years in demolishing everything. So we're very sparse on any glacial deposits here. So that's what the paper gonna looked at. And so traditionally people thinking this is the glacial stuff, we can date it and we can tell when the last time glacier was here. But the new research come out and the people talking about, no, it could be not come from the glacier, it could come from the slope and form the landslide. And I'm talking about this before, and actually my research was related to that too in my previous video and discussion as well, so you can go back and check it out. So let's have a look on the abstract. So the ambiguous landscape histories, so these reconstructions or interpretations which might be not true, can arise from incomplete geomorphological, sedimentological, and geochronological evidence. And that's the main sentence which summarizes all the paper. So if you have some kind of suggestion about a region or formation of particular hill or slope, all your ideas what's happening in the valley, in the country, or even geology, historical time in that area could be wrong. So here we see they proposing analysis to robustly assess the region and age of a field of rounded mounds. They're called mounds, hills, yeah, hillocks, known as hillocks. We're using cluster analysis, sediment. It's consistent with landslide region, but inconsistent with other glacial sediments in the region. So the very outsiders there, these hills, whatever material within, it doesn't match anything surrounding, and that's kind of question mark. cosmogenic beryllium 10. So this is the dating technique we use. Cosmogenic, it means the air radiation that comes from the space, this kind of background radiation, not from the sun, but background in the space. There's a lot of radiation. It could be detected, and it's coming onto the Earth, and whatever this on the surface, being bombarded with this. And beryllium, which we can find in quartz material in the rocks, will be decay because of that, because of this radiation, and we can pick it up in a lab and figure out how old this rock by knowing when this quartz particle start being exposed to the space. So when it's come out on the surface. For example, if you had ice, when ice melted, that will be the time when this rock quartz start being exposed to the space. Yeah. So if my dates tell me 6,000 years, so 6,000 years ago, last time this rock been covered. Doesn't matter, landslide or glacier, or somebody was just covered it. They use also, they find out that it's about 8,000 years. The penetrating radar reveals the deposit rest upon deltaic forested beds. And I just lost my line. And and with topographical data they calculated the volume of these deposits about from 15 to 27 million cubic meters. And that's kind of nicely matching with what they suggested, because they proposed the source area in the mountains where it's actually come from as well. So they're indicating that a region of rock avalanche deposits, and it's about 8,000 years old. And at that time, the level of Lake Wakatipu, so the level, as I told you, will depend on this ice melted, and the water level in the lake actually will be changing. Depends how much water going into. And the lake was lower, 340 meters by that time. And they're talking about the shoreline, so that's the basically summary. These findings are significant given the lack of landforms by which to constrain glacial or post-glacial landscape histories in this region of New Zealand. So in New Zealand, in some places we have a lot of good deposits, in some places not, and people drawing conclusions from the suggestions. So have a look. Let's have a look on the Google Earth where it's located. This the New Zealand, nicely located in the middle of the ocean. Actually, it's located between two oceans, Pacific and the part of the Indian Ocean. Yeah. Okay, I hope the live's still going. Oh no, I didn't switch. Yeah, that's what I didn't do. Little meandering around. So that's the New Zealand and Pacific, and this the Tasman Sea, which supposedly the part of the Indian Ocean. And we're talking about South Island, and we're going into this area, kind of south central part of the South Island, where the Wakatipu Lake is, and it's a little bit crooked like that. Most of the lakes going straight down to the south, but that one a little bit twisted. There's a more complicated geology in that area, if you can see. I talk about a lot about geology of Southern Alps in my previous videos. You can have a look in history of formation. We talk about Castle Hill Basin in specific, talk about schists and rocks in mountain formation. So I have good videos about that. I can send you there. But you can see here briefly, if you don't want to watch those videos, there's a fault coming through. It's quite straightforward. You can see it from the space, I believe. I haven't been in space, but probably you can. And if you look closely, look, it's a very straightforward line. And the highest mountain peaks a little bit east from there. I don't know, maybe 20 kilometers or so, but that's the highest peak. The Mount Cook is here. I talk about this a lot when I talk about glaciers, all the lakes of the glaciers, and about geology. I love this area in particular. And we have a lot of valleys, and further south we're going to this Wakatipu. So you see those actually glacier which preserved, they closer to the Alpen fault, and they were fed by this highest peak of Southern Alps, similar like Mount Cook region. And then we have these two kind of big valleys that's feeding the Wakatipu. That's the Queenstown, party town. Well, it's not party town, but people go in there, especially in the winter. They ski in there. People go there in the summer, do a lot of jet boats and this kind of stuff. So it's very popular. There's a big airport, you can see here. And this nice peninsula, I think there's a golf course, and even that's why they filmed Lord of the Rings, I have to say that. And we have the Ara Valley. It's a little bit kind of up the stream. You probably will travel here if you're going to the west coast through here, but usually people take different routes. Glenore here, it's somewhere there, and I turned off all the names, so otherwise be too busy, but I preserved the pictures and we'll have a look. So that's the shore of the Lake Wakatipu, Kinloch. Wow, it's a good image. And yeah, by the way, this is all copyright probably, so don't take offense. I'm using it because it's for free in Google Earth. You put it there. They say Isengard Lookout. It's probably been in the movie too. And we see this very braided river called Dart River. Very nice, interesting name. Already clicked this. Yeah, and it's very plain. You can see there's not much. So this is all river deposits which been reworked by the river since glaciations, top of the mountains. A lot of farms, people use it. Farming. This second river join in. I forgot the name, so I'm not gonna put it. Stables, okay, very lovely. And then we have these hills, and even from this image you can see they're there. But one thing that will strike you the most, look at the river. So it's going from the north nicely, taking quite wide extent. So it's going from shore to shore. It used to be here, but then it's been diverted. You see this, now there's like a little lake, I believe. Diamond Lake, yeah. So there used to be a stream going through, and then something happened, it's changed the catchment, but the water stayed there. So it's very common in New Zealand, especially around Southern Alps. There's a big bedrock, Mount Alfred. Oh, there's an amazing view from top of that, and this is actually a view on the hills I'm going to talk about. So this, somebody standing on top taking photographs. That's the bridge going through, and these people see this there. So if you're going there, you're going to drive through this bridge and you see those hills, yeah? So you might see, oh, it's something normal if you're not geologist, but the geologist will straight away thinking, oh, where it's come from? Because look, everything is here is flat and reworked by the river. And you see the river here almost taken from shore to, mountain to mountain. This used to be old river as well. Passage, and you see there's a little swamps leftovers, and then people of course regulated it all now. Yeah, so the Hero River brought a lot of material here, and she kind of spread into two directions. But this is for fluvial people. They love this kind of stuff. But look at the river, what I want to say. Yeah, that's the view. Very beautiful blue water. You have braided, and it looks like it might go through, just straight through, and it will probably, would, I would say. But something happened, and you have a lot of material here, and the Pool River have to redivert, change its course, and go around it. And you see she went all the way till the opposite slope and back to the middle, you know, this valley. And this valley not very wide, and if you can imagine, I love the Google Earth. It doesn't show you, unfortunately, but I have the ruler. I don't know why it doesn't do this. It doesn't do on a live stream or recording. Maybe it's the OBS Studio. So I put the ruler from road on the left side to the right side, and it showed me 1.6 kilometers. So it's not very wide area, and that's what's happened. So scientists suggested this is the landslide. So the slope collapsed, and we probably can have a look where from here down. It's a little bit exaggerated, my topography here, for better perspective, but you can imagine. And it's fall down here, and it's blocked the river for some time, and then she went through here. And on this picture, which we've seen before, you can see it when it's kind of wind around some slopes. So here maybe we see the source. Probably it's there. So lovely. So that's the settings, and we're going to talk about this lake, how it's affected it. And in the past there was all ice, as I told you, and that's the moraine, terminal moraine, the end moraine I talked about, which the city is now on, I believe. It's not very straightforward. Sometimes these moraines could be quite tiny. Yeah, I believe it'll be somewhere here, these ridges. And it's all been dated before, and people trying to understand how it's related or the same like in the Northern Hemisphere, yeah? Like in European Alps or Scandinavian ice sheets or even North American ice sheet. And it's not just a question of that, it's also about how we interpret it, what we see in the field, how detailed we should study, things like that. That's the main point of this paper. And for you, might be not end of the world, but some scientists would spend all their life dating and writing papers. It could be quite significant. When somebody say, you know, all your work is not true. Yeah. All right, so let's come back to the paper. Let's go through. So the introduction, it's a very nice introduction. You can read it, even from my live stream, if you wish. Just check my sound. What's going on? So glacial chronologies, landscape histories, and hazard assessment must be underpinned by a reliable assessment of landform origin. That's just what I talked about before. So the glacial landform, it's moraines, and they're quite similar to landforms that are produced by the landslides, and that's I talked about before as well in my paper. But it could be geomorphologically similar, so like appearance is similar, but the sediment, the material could be different. And that's why people confuse them. But often people just don't even go and look on the deposits, they just map it from satellite images or something like that. Now Google Earth, they date it, they don't even look on the material itself. And often you cannot, you just go there and they're just hills. So if I go into my original image, you know, if the river will not cut through and I see actual material, what can you tell from this? Okay, some kind of rolly hills. I don't know what it's inside. Is it the bedrock? Is it the sediment? So you have to go and investigate. Yeah. So let's come back to our paper. So there's a very nice introduction. So we should differentiate, they say. In this study, we investigate the Hillocks. We already know that. And we argue it's produced by rock avalanche. And apparently sounds like it's a second paper and a little bit modified and improved with new dates. So they have new cosmogenic dates, which assess whether or not the landform age is consistent with the late glacial origin as previously assumed. And it's bring light, shed the new light on the post-glacial landscape evolution in this part of New Zealand. In New Zealand, Southern Alps very active, so there's a lot of earthquakes. And slopes quite unstable because just recently there was all glaciated, and you can see they're all steep. A lot of it there's a schist, and I talk about this in the geology of New Zealand, Southern Alps in particular. So they can imagine they're quite active, so they're falling down all the time, slopes, rocks, and the rivers modify them. And we still have this deglaciation rebounding when the rocks kind of like become free from the ice and everything, they've been loaded on them, and they're relieving this stress now, and a lot of landsliding happening. But with New Zealand earthquakes, it's not a biggie. Just have a big earthquake and then couple good torrential monsoons. We have this rain season, especially last several years with La Nina, and you have a lot of landslides as a result. So regional settings, we talked about this. I'm not going to go in detail. We've beautifully done map. And in scientific papers you usually have to describe geology. They talk about this type of the rocks that you can meet there. They talk about geology. They're talking about what's happened with the glaciation. So it's catchment that fed into been glaciated during the Quaternary period. And today's 6-kilometer long Dart Glacier sits at the head of the Dart catchment, and that's the one that I showed you on top of it. Actually didn't zoom in. I think this is the Dart Glacier here. Quite small now, but used to be all over in the valley. Just need to come back to my original settings. Yeah, that's better. All right, so let's come back to the paper. And yeah, they're talking about glacial erosion, Tyrian terminal moraine. This is one kind of like last LGM, last glacial maximum moraines. A moraine is just a glacial deposit, yeah. And then he talk about the sea, the level of the water in the lake, and it's kind of, it could be important because when you're trying to understand how much water was in the catchment, how much displacement happened, so how much ground actually rised or deepened, all these things, and the level in the lake will different. So they're saying here, let's just read. So there's evidence represented by stranded lake shorelines, alluvial fan terracing, and delta faucets that Lake Wakatipu was previously been up to 50 meters higher than the present day. Radiocarbon dating of wood excavated from one of the shorelines cut 26 meters above the current lake level suggested the lake was at the level at about 10,000 years before today. Yeah? The highest preserved shoreline, 50 meters above the modern lake level, is suggested to have formed at least 1,000 years earlier. So little information is there. And we see some of the delta, like Wakatipu Forsets beds preserved east of the Mount Alfred at elevation 358 meter sea level. And it's about 10 meters above the modern Dart River floodplain. So that's what we have so far. So the methods, they looked in deposits, morphology, sedimentology, geophysical, and chronological tools. So they use dating, so they date the rocks on top of these quartz. They did collect the samples and looked at the sediment. I talk about this about my research very specifically. Morphology, so they assessed where the hills can be found, how they aligned, how many of them preserve, this kind of stuff. Where the potential source of the landslide, and calculate is it matching the deposits or not. In geophysical, here we're talking about actually grain penetrating radar. So when you scanning through the earth, and by the differences of how the wave penetrating through, you can see with the different medium, and then you can figure out, oh, this is this material there, or there's a water or something else. Sedimentology. So this is very classical. I looked through 50 clasts they collected. Traditional among glaciologists or just geologists, we're looking on the rocks, the shape, the angularity, and we create statistics, and then we see if these rocks more look like glacial or come from river or from the slope, this kind of stuff. So to talk about this here, we looked at a picture of the results. Age assessment, so they took date the boulders. They have some from accumulation area, so where the actually rock avalanche come from. They have some on the way and from the fence they've been creating since, so they have a little bit like a backup plan. So they didn't just date the hills, but other material around it. And they say you can read specifically in detail where they analyze the samples, how, and it's pretty standard for this. So they took samples, crush the rock, you do crush the rock, separate them, and then there's a lot of chemical washing going on. It takes several days, and then when you took this beryllium out, you take to the accelerator mass spectrometer. We have one here in New Zealand, GNS Science. There's one in Australia as well, and it gives you the date, approximate date. That's the beautiful site. So this the rocks that they dated. So they're looking for these quartz veins within, if you can see. And then they estimate how the slopes, for example, this rock exposed to the slope, to the space, and when it's morning or evening or whatever, it's shadowed by the slopes, and then they estimate for our latitude, how far we're from equator, or this kind of stuff, so how we're exposed to the space. And there's a standard procedure, so you use some kind of methods or develop your own. Subsurface investigation, it's the grain penetrating radar, or GPR we call it. It's quite complicated. Well, it's not complicated, but it's heavy and time-consuming thing. So you go there and actually doing these measurements. But it gives you a beautiful image, and we can have a look here. So I don't have to talk about this. It looks like that. So this is just a wave. So this line on top, it's kind of air between radar antenna and the ground, and then you start seeing surface. So these kind of waves show you different angle, different material, and something will the wave gonna go through faster, something fine or wet or something like that, and then if you have big boulder or heavier material, different strata, for example, if you have sediment and underneath you have bedrock, solid rock, so there'll be, you see the border, the difference, and that's what they're showing in this image. You can have a look in detail and read the description, and it's actually give them information how deep it is and how far it goes. We talk in detail of what they use for that, which methods and programs, and the volume and morphometry of the deposit. So they get nice, created nice images. They use the aerial LiDAR, kind of scanning through, so you can see the topography without vegetation. Modern days you can do it with a good drone. You just fly it over the area, but it's all equipment, money, and time, and you need to know what you're doing. So they assessed everything, built the map, and then they will see in the results section what they estimated. So results, sedimentology. So pretty much they write down this angular class, supported, poorly sorted, and lag bedding structure. So it's very typical for a landslide. We actually, let's have a look on the pictures here. This is how it looks like. So it's one of the hills cut through, and you can see the very different class. So you have bigger things in between, smaller, and very angular, and you can see it's same lithology. Even here, without without looking at the actual material, we can see that it's all similar, same actually lithology. If it was glacial, it would be everything represented that in the catchment. So there will be rocks. They'll be more sorted, so it'll be more rounded and kind of more aligned, rather than like that. And they will have a different color, for example, like sandstones, mudstones, a little bit of quartz or something else, or volcanic rocks, everything will be more aligned. And there's a lot of fine metrics, which is very important when you have a big landslide. So here we can see the results of the sediment, hillocks. It's quite angular, poorly sorted, and you can see it's very nicely matching to not even glacial, not even close to the glacial, sorted, rounded, and kind of sift through with the water, a lot of water mixing substratum. So now these ones are quite not that sorted. So it's quite straightforward that it's come from something else. For example, one event, rock avalanche. They're talking about dating, so the dating, not going to the date, but age assessment, correct name for that. And I talk about a little bit about dating techniques. I want to make a bigger video about cosmogenics. Oh, no, I don't want to do this. Cosmogenics, and they use beryllium, so you can, if you're interested, write me comments. Yes, we want a video about that. And here, if you learn more, you will be easy to understand what they're talking about it here. So we will read in results and subsurface information. So they did this GPR, as I say, and calculated approximately the size of the deposits. And this is interesting. This is your dating result. So they also did the Schmidt-Hammer. Schmidt-Hammer, it's so interesting. It's the German interesting system that people start using. You know, people using Schmidt-Hammers to test it if you're, for example, you have a metal surface or I don't know, sheet of metal or something, you want to build buildings or use it in industry. And the Schmidt hammer is little like gun equipment. You shoot it through the surface and it shows you how weathered or how weak the surface is, how it's going to be exposed, how it's going to be deteriorate fast or not, how resistant it is. That's what it is. It's very simple, kind of mechanical. It's just shoot it through and it show you the gradient, the number. And people start using it in geology, so they go on the rocks and they smash them with the Schmidt hammer. Well, it's not actually smashing, you just point it and you press the button. And they give you the reading. And if you go through one deposit, it should everywhere show the same reading. And if something different, it will be all different lithology of that rock. It's mean, for example, some rocks more harder and they preserve longer, some more loose and they'll have different readings. But it also means that this rock might be from something else. So, and been here older and been lying in the valley all longer and been exposed to erosion and have a weaker surface. So they did Schmidt hammer. I didn't know, it's kind of funny. And then they did exposure age as well here. And they show this, the mount is actually this hill, so the one hill, second hill. So it's all kind of within debris fan, a little bit younger, which obvious, it will be younger than the deposit. Deposits first happen and then the debris fan build. And we have the source area kind of matching with the hills. So, and it's all about 7.88 thousand years ago. You see, it's quite a big difference, but it's also the method, how we calculate it, it's so complicated, so there's so many factors included. So if we have about plus minus 1,000 years, it's good enough, isn't it? The more we go into the past in the science, the more we're talking about these kind of things. We're talking about thousands and millions of years, plus minus. In the modern days, we will talk about months and days, even seconds and minutes. So that's the difference of our time perception. And it's also how hard it's to go into the past and exactly know what's happening. Unless somebody put the watch into these deposits when it's happened, with the date and time, we'll never find out exact date. So we talk about the volume, they estimated it. There's a very nice info about the elevation of each of the hill, how it's aligned, a very detailed work. And they have a discussion about the origin. So let's see how much time we have. I wouldn't have much time. I don't have much questions. I don't have any questions. Nobody watching me because I didn't announce myself. So let's just go through discussion. So they speculate, of course, that it's landslide origin. Where did you say that? Volume and source. So they suggested quite a big volume, and it's quite typical for this landslide that can happen. And it's kind of matching our source. So that's the alignment of the hills. That's the profile topography from T to T, so one direction and perpendicular. Implication for landscape development chronology, that's what we need to look at. So they're saying that the Hillocks is a landslide deposit, has implication for understanding glacial and post-glacial landscape change in this region. First of all, it'll tell us that it's not glacial deposit. Hello. So we don't know if the glacier was there at the time or not. Another thing, that the landslide happened 8,000 years ago, so it means the ice was already away from there, because we still have it there. If there was ice, it'll be reworked or moved away. That's another good implication, yeah. I don't know if it says here. It should. Yes, provide some constraint on prehistoric timing positions of the Dart River Delta and the level of Lake Wakatipu. I think they're more focusing on the level lake water level. And I think because the author's involved in some other work about this level and shores and terraces and the lake, so that's why they kind of emphasize it here. So we have a constraint on the maximum delta progradation rates of 1 kilometer per 1,000 year, and average since 8,000 years ago. they also say about surface and abandonment may relate to a blockage of that river by the rock avalanche, which we talked in the beginning, possibly driving temporarily ponding and a gradation upstream. And we can see this, can we? We can see this on the Google Earth. That's what I talked about when we have this kind of like, that's the temporal blockage. But I think this probably won't be related to the landslide. Although it could be that it's blocked it and then the rivers find a way through here before it's cut through. It could be. But I think that one related for previous, when the ice was here in the area. We have this interesting lake here as well, and the way how the river developed, you know, upstream. So that's what they're saying here. Maybe you don't need it in such a detail, which I've talked about, but we're going through the paper, why not? So let's have conclusions. What have the conclusions? That's a very important part of your paper. You can read abstract and conclusions, you'll be quite sweet if you don't have time to read through all the paper. And only when you start analyzing something specifically, you will go through every word and details for the paper, if you're working on the site, if you cannot find some information. So scientific paper could be versatile. You can use it for different things. You can just read the titles and make your conclusions, or you can go in detail as much as you can and make your conclusions. So the information of morphology, sedimentology in this study favor rock avalanche region. We know that. The class morphologies within hillocks are consistent with rock avalanche deposits, but not with other proposed deposits or mechanisms. The morphology and distribution of the mound suggests thinning of the deposit and reduction in mound size in a cross-valley direction away from the proposed source area, and that's normal for landslide. That's where they build those profiles to see. The most plausible source area identified for the landslide seems to be the basin to the west, which has a scar with a volume compatible with the volume measured for the hillocks. And it has produced boulders with the lithology matching that of the hillocks. So the rocks, the source volume and geology matching what we found downstairs, down the valley. So that's what they're saying, and that's why they did such a detailed work there. If you wonder, GPR data indicate that the deposit was emplaced upon a braid plane and prograded delta. So it tells us there was no ice already in the valley when this happened. So it just went down over the river material. And our dating, beryllium 10 exposure day age, give us about 7.9 thousand for the mounds, and statistically indistinguishable ages for adjacent landform assumed to be related, provided further support for rock avalanche region. Yeah, that's it. Basically, it's confirmed it. But it's nice to have a date now. Let's indicate a Holocene timing for that event. So 8,000 years ago, I have a video about Holocene. You can see what's happened in Europe at that time, and there was a Dart landslide happened in New Zealand. Hopefully nobody has suffered that time when it's happened. Nobody was covered. What else they say? The new data that 8,000 former Wakatipu glacier had certainly related up valley past this location, and that that river had prograded down valley of this location, providing useful constraints on glacial and post-glacial chronologies in the otherwise fragmentary record of events in this catchment. Furthermore, this study demonstrates the utility of quantitative methods of landform identification and analysis for informing studies that utilize landforms for paleoclimate or landscape reconstruction. So that's one of the points of this paper, that we can detailed look at these deposits from all aspects, and dating, and where it's come from, and morphology, and lithology, and GPR, and how it's related to what's happening around it, and only then we can draw conclusion about climate change or what's happened with the glaciers in this area. And there's a very good list of reference, which are important and used in this paper. So that's the paper, and I'll finish now for that. So thank you so much for joining me today, and like it, subscribe, share it, and I will see you in my next videos.